What are they like? Well, they're quite a lot like this. They describe a thing to build and they give you some kit to build it with. And then what you have to do is remember what the kit does, figure out how the description corresponds to some evolving behaviour, figure out what control signals will produce that behaviour, and then figure out the circuitry that will produce those control signals. Let's apply that method to this problem from the recent test 4.2. The one where Mex Locke is trying to get two computers, numbered 0 and 1, to share a printer. So they control input signals P0 and P1, and they send a 1 on those signals at time t if they want to access the printer, and from time t plus 1 onwards. And they send a 0 if they don't want to access the printer. If they're not competing for the printer, then they should get what they want. Once a computer starts printing, it should keep the printer as long as it wants. If neither is printing, but both suddenly asked to print, the computer which printed most recently should give way. So that's a description in words of some rules for deciding whether somebody prints, and if so, who. We then get told that the machine so far that's been built has these bits and pieces in it. So you can see it's got a D flip-flop and with output Q, and a JK flip-flop with output Q prime. And the idea is this, that if Q is 0, that means nobody is printing at the moment. But this flip-flop remembered who had the last go with the printer. And if Q is 1, that means that somebody is currently printing, and Q prime will be 0 or 1 according to whether it's computer 0 or computer 1 that's printing. And the helpful thing, rather than a complication, is that Mex Locke, the designer of this machine, has built two muxes into the controls of the JK flip-flop. And the control line of the mux is connected to this AND gate, which detects whether both computer 0 and computer 1 want to print, because the logic for that's going to be different. So here, on these two mux inputs, we get the J and K signals if there's no competition, and on these two mux inputs, we get the logic for resolving a dispute, and that depends on whether anyone is currently printing, and if so, who had the last go, exactly as the description suggested. Okay, so let's figure out how to turn all of that chat into a more formal description of some behaviour that we might be able to build a circuit for. Let's draw a characteristic table whose inputs are the inputs for the circuit at time t, so we tabulate those, all the possibilities. Nobody wants to print, computer 1 wants to print, computer 0 wants to print, they both want to print. Okay, and then we better say what's going to happen at the next time for Q, whether we're printing or not, and for Q prime. Alright, so let's just work out the logic. If nobody wants to print, then nobody will be printing. If computer 1 wants to print and computer 0 doesn't, then it'll get what it wants. Otherwise, if computer 0 wants to print and computer 1 doesn't, then somebody will get to print. And if they both want to print, then indeed somebody will get to print. But we don't know who. Now, working over here, if nobody wants to print, then Q prime is supposed to tell us who printed last. And who print under the situation that nobody new wants to print, then whoever printed last will stay the same. Meanwhile, if just computer 1 wants to print, then somebody will be printing and it will be computer 1. If just computer 0 wants to print, somebody will be printing and it will be computer 0. And if they both want to print, if there's a competition, then the logic is a little bit more involved. that it depends on whether somebody is currently printing. If somebody is currently printing Q of t, then they should stay printing. So that means Q prime of t plus 1 should be the same as Q prime of t. If Q of t is true, then Q prime of t tells us who is currently printing, and they should still be printing. Otherwise, if nobody's printing, then the person who gets to print should be the opposite, the negation of whoever it was printed previously. So that's the logic for this box in the characteristic table. Okay, so we've figured out how to tabulate the behaviour we want from the given inputs. Now we need to find the control signals for that. And at this point, we're going to need to remember how the actual flip-flops work. So let's do the first two parts of the question. We have to write down the characteristic table for a D flip-flop. So that's to say, when we know what D of t is, we should be able to say what Q of t plus 1 will be. And for all possible inputs, 0 and 1, we give the behaviour, which in the case of a D flip-flop is just to echo the input 1 unit of time later. For a JK flip-flop, whose output is Q prime, we have to say how Q prime, not Q, will evolve depending on what J and K are. So again, we tabulate all possible combinations of input signals, and we explain what should happen to the output. If we send in 0 on both input signals, the flip-flop should stay the same. And that means that Q prime of t plus 1 should be Q prime of t. If you leave the prime out, you're saying that Q prime of t plus 1 should become what the D flip-flop is storing. The name difference does matter. If we're saying reset but don't set, then we go to 0. If we're saying set but don't reset, we go to 1. And if we say send both at once, then we toggle. So that means that it's not of Q prime of t. So those are the behaviours that our flip-flops can do, and these are the behaviours we want. So we're nearly there. We have to figure out how to send appropriate signals, D of t and J of t and K of t. Okay, now we can see clearly from the characteristic table for the D flip-flop how to get a 0 or a 1 out. You put a 0 or a 1 in, so the D column should be the same as the Q of t plus 1 column. The D of t column should be the same as the Q of t plus 1 column. These two are equal. For J and K, we look at the Q prime of t plus 1 column. Here, we want Q prime of t, so that means we need to tell the flip-flop to stay the same, which we do by sending in 2 zeros. Here, we want the flip-flop to set, so we send in a 1 and a 0. Here, we want the flip-flop to reset, so we send a 0 and a 1. And here, we need to see what the right behaviour is. We want to send the toggle signal if Q of t is 0, so 2 1s here if Q of t is 0, or the stay the same signal, so 2 zeros if Q of t is 1. That means in both of these places we are sending exactly the opposite of Q of t. So now we have our table telling us how to construct the control signals from the inputs and, if necessary, the current values. So we'll see if this cut works. But right, So now we have the table which explains how to give the values of the control signals. We should be able to build the circuit. Let's start with the D flip-flop. We can see here that we've got to deliver this truth table for the D flip-flop, and hopefully you recognize that this is just the truth table for an OR gate. So let's say that the idea that if at least one computer wants to print, one computer will get to print, is being captured by that logic. Okay, now the muxes really help us here because it allows us to separate out this part of the JK problem where there's no competition from this part. Let's look at it. Up here, so this column corresponds to this box. We have to make sure that we deliver these signals, but as far as that box is concerned, it doesn't matter what happens when there's competition because the mux will ignore that signal anyway. So the easiest way to make something that looks like this is to notice that it corresponds to the P1 signal. That's to say that computer 1 is going to try to send the set signal. So what we have to do is wire computer 1 into the mux. And similarly, we can see that this column, as far as the first three rows are concerned, just agrees with signal P0. And it doesn't matter what happens if there's competition. So that's to say that computer 0 is trying to send the reset signal. Now what happens if there's competition is going to be determined by what's in this box, because that's when the mux pays attention to these two inputs. And we can see that they're going to be equal. They have to be equal because the wiring doesn't give us any other choice, but fortunately for us, they are equal, and they're equal to the negation of Q of t. So all we have to do is put a NOT gate in between Q of t and the output of that circuit. So the other wires are just ignored, and we've completed the logic. Let's just check that it fits with the description. If either computer wants to print, one computer will get to print. If there's no competition, then computer 1 will successfully set the flip-flop, the JK flip-flop. If there's no competition, then computer 0 will successfully reset the JK flip-flop. And if both the computers want to print, then if somebody was currently printing, they will stay printing because J and K will both be 0, and if nobody was printing, then the JK flip-flop will toggle, because if Q is 0, then J and K will both be 1. So we have delivered the specification exactly as required. So what was the plan again? Read the description, remember what the kit does, figure out how to translate the description into a table that describes the behavior, use the definition of the kit to figure out what the control signals have to be, and then build the circuitry that delivers the control signals at time t from the inputs at time t, and if necessary, the current state at time t. So that's a fairly direct application of the method for doing flip-flop construction.